triangle proportionality theorem. It's also called side splitter theorem, right? And basically what it says is that if a line parallel to one side of a triangle intersects the other two sides, it divides the two sides proportionately. So the parallel line splits the sides proportionally. So we go down one side and then down the other. And just like we had to match corresponding parts when we were solving with similar triangles, we have to match corresponding parts. So RT goes with TQ. So RT over TQ equals RU over US. So one side in one fraction, the other side in the other fraction, and then match them across. Right? So RT and RU are across one another. Right? So RT and RU are in the numerator. TQ and US are across one another. TQ and US are in the denominator. All right? Let's solve a problem so you see how it works. All right? And it doesn't matter who's in the numerator, who's in the denominator. Be consistent. All right? So I'm going to start here. All right? So I'm going to put CB in the numerator, and that corresponds with BA, right? So CB and BA are on the same side, I should say. All right, so I've got the blue side there equals, and then we've got the other side, CD and DE. So I've got one side of the triangle in one fraction, the other side in the other fraction, and notice CB is across from CD. They go together. BA is across from DE. They go together. All right, so now let's just plug in the values. So CB is 10 and BA is 5. CD is 7 and DE is X. And now we'll just cross multiply. All right, so 10 times X is 10X equals 7 times 5. So that's 10X equals 35. Divide both sides by 10. X is 3.5. By the way, you could have reduced if you wanted to. I'll just show you. 10 over 5 equals 7 over X. So 5 divided by 5 is 1. 10 divided by 5 is 2. I'd get 2X equals 7 times 1, of course, which is 7. And then divide both sides by 2. X is still 3.5. All right, so you solve using a proportion. Go down one side, then down the other, and match them across, and you won't get it wrong. That theorem also goes the other way. All right, so we can, if we know the sides are parallel, if we know that line and that side is parallel, then we can use side splitter theorem. But if we know that they're in proportion, then we know the lines are parallel. So we're going the other way. Right? So now we're seeing if the lines are parallel. So this is the converse of the triangle proportionality theorem. If a line divides two sides of a triangle proportionately, then it's parallel to the third side. So if a triangle is divided proportionately by a line, the line is parallel to the third side. So if RT over TQ equals RU over US, then TU is parallel to QS. So we're going the other way. Right? Before we knew the lines are parallel, so we can solve for the missing part. If the parts are in proportion, then we know the lines are parallel. And it's the side of the triangle and the line that splits it. All right, so now let's see. We want to find out, is PS parallel to QR? If it is, then PN over PQ will equal NS over SR. Now you can do this one of two ways. Right? Here's way number one. We're going to see if the equation is true. In other words, do we get the same thing on both sides? So for instance, if I got 1/2 equals 1/2, well, that would be a true statement. Let's go move this down. All right, so Pn, so let's plug the numbers in. So Pn is 90, and PQ is 50, and NS is 72, and SR is 40. So now let's reduce. All right, so, well, I can cross out the zeros, right? So that's 9/5 equals, 72 and 40 are divisible by, they're both divisible by 8. So 72 divided by 8 is 9. 40 divided by 8 is 5. That checks out. So because 9/5 does equal 9/5, we know the sides are parallel. Right? So let's write that. So because Pn to PQ equals NS to SR, the sides are split proportionately and according, and I'll put that at the end, and PS is parallel to QR using the converse of side splitter theorem. All right. Here's the other way. See if the cross products are the same. See, this is really easy to reduce, so that was fine. But if this is really hard to reduce, then maybe it would be better to see if the cross products were the same. We start off the exact same way. All right, so 90 over 50 equals 72 over 40. Now, the only thing about this one is the numbers are a little larger, right? So reducing was probably easier, but I just want to show you another way. 90 times 40 equals 72 times 50. All right, well, this one's easy. All right. That's 3,600. And then 72 times 100 would be 7,200. 50 is half of that, so it's going to be 3,600. And you can check my math if you want to. That does check out. So we also could say, and actually, I think we can use the very same, because those cross products are showing it's proportionate. Right? So whether you use the cross products or whether you reduce your fraction, either way, I want to move this over. Either way, you can justify it the same way, that because Pn over PQ is equal to NS over SR, right? Because we know it was true whether we reduce the fractions or whether the cross products are the same. The sides are split proportionately. Come on, move over. Oh, so close, so close. There we go. The sides are split proportionately, and PS is parallel to QR using the converse of side splitter theorem. There we go. All right? And that's all there is to this problem. Let me check and see if I've got any others, if this was the last one. It was the last one. Thanks for watching. Bye for now.